Okay, so this is another article I found interesting. Today is Tuesday, August the 18th, 2020, and another article from sciencealert.com in the physics section. The force of nothingness has been used to manipulate objects by Michelle Starr, published the 7th of August, 2020. Let's see. Scientists can use some pretty wild forces to manipulate materials. There's acoustic tweezers, which use the force of acoustic radiation to control tiny objects. Optical tweezers, made of lasers, exploit the force of light. Not content with that, now physicists have made a device to manipulate materials using the force of nothingness. That sounds very interesting, right? It's the first time I've ever heard that. Okay, that may be a bit simplistic. Tell me about it. When we say nothingness, we're really referring to the attractive force that arises between two surfaces in a vacuum, known as the Casimir force. The new research has provided not just a way to use it for no-contact object manipulation, but also to measure it. The implications span multiple fields, from chemistry and gravitational wave, astronomy, all the way down to something as fundamental and ubiquitous as metrology, the science of measurement. You know what, you guys? I found this interesting because I wonder how things like this sometimes can be used to create like quicker transportation when it comes to like train tracks and other things, just like quicker forms of transportation where you have like the negative force between two objects and they can travel, and never actually touch. But that's just what I'm thinking about right now. Moving forward. If you can measure and manipulate the Casimir force on objects, then we gain the ability to improve force sensitivity and reduce mechanical losses, with the potential to strongly impact science and technology, explained physicist Michael Tobar of the University of Western Australia. The Casimir force was first predicted in 1948 by Dutch theoretical physicist Hendrik Casimir, and finally demonstrated within his predicted values in 1997. But since then, it has been generating a lot more interest, not just for its own sake, but for how it might be used in other areas of research. What Casimir predicted was that an attractive force would exist between two conducting plates in a vacuum, due to contrast and quantum fluctuations in the electromagnetic field. To understand this, we need to delve into the weirdness of quantum physics. In reality, a perfect vacuum does not exist, even in empty space at zero temperature. Virtual particles like photons flicker in and out of existence, Tobar said. These fluctuations interact with objects placed in vacuum and are actually enhanced in magnitude as temperature is increased, causing a measurable force from nothing, otherwise known as the Casimir force. Okay, it's starting to make more sense. The team's experiment took place in room temperature settings. They made use of a tiny metallic enclosure designed to confine certain kinds of electromagnetic radiation, referred to as a microwave reentrant cavity. Separated from this cavity by a gap of about 1 micrometer was a metal-plated silicon nitride membrane acting as a Casimir spring. By applying an electrostatic force, the team was able to control the reentrant gap with exquisite precision. This, in turn, allowed them to manipulate the membrane with the Casimir force that arose when the gap was sufficiently small. Because of the Casimir force between the objects, the metallic membrane, which flexed back and forth, had its spring-like oscillation significantly modified and was used to manipulate the properties of the membrane and reentrant cavity system in a unique way, Tobar said. This allowed orders of magnitudes of improvement in force sensitivity and the ability to control the mechanical state of the membrane. But controlling the gap also allowed the researchers to measure the force. As the gap opened, the Casimir force grew weaker, until it was at a point where it was no longer acting on the membrane. By studying the changes to the membrane, the team could generate high-precision measurements. It's a novel way of measuring nothing, though. Other methods have used tiny, rapidly moving materials to also get a grip on the force exerted by variations in otherwise vacant quantum fields. Other studies have also put the force to use in less precise ways, helping tiny silicon devices keep their distance, for example. The technique presented here has high potential to create additional schemes and devices by manipulating the thermal Casimir force, the researchers wrote in their paper. For example, in situ, agile programmable devices engineered to manipulate mold structures and improve resonator losses as needed at room temperature could be constructed, including the development and manipulation of topological mechanical oscillators. Doesn't that sound fun? A little bit. A little. The researcher has been published in Nature Physics. Alright, that's interesting. We'll see where that goes in the next couple of years.